Hello, everyone. If you do not know my uh, cats, this is Frances, and I think she's the greatest thing in the world. I love her an awful lot. She doesn't like this mouse that's right beside her, but this is my baby. Watch her sleep. Not the whole video, obviously. Alright, so you saw my cat. Now I want to talk about forces and potential energies and energy in general. So I want to define what these conservative forces are, and I say that they're independent of the path. What I mean by that is, let's pretend I'm going to throw an object, and it's going to go from this height to this height. I'm going to give it some initial velocity, v initial. It doesn't matter what particular angle I throw the thing at. Right? What's going to happen is, on this green path, it's going to get down here, and it's going to have v final. But on this purple path, I throw it basically upwards at a shallow angle, and it slows down as it gains height, but then it falls back, and at this point, it'll have the same V initial, and then so when it gets down here, it'll have V final. And when it jumps up here, it'll slow down a lot more, but it'll still get to 0 at its maximum height, and it'll come back down here, and it'll have V0 there as well. So when it gets down to here, it'll be V final. Right? And we talked about this a little bit, calculating, right, the idea of calculating the velocity. Well, the velocity looks like V initial squared plus 2a delta y. But this doesn't tell you anything about where this goes. So if we do this with kinematics, we would get that there's the same V final down here no matter what the path is. Now we would get different heights for these V initials for these velocities being 0, but ultimately this H initial having V initial here results in this H final having this V final independent of the path. The only thing that seems to matter is this particular force and this particular displacement. So what this is a statement of the kinetic energy, right? What we're really saying is delta K here is V final squared minus V initial squared, that part of it. So it's just 1/2 mv final squared and 1/2 mv initial squared. Equals, well, over here, this is really minus mg delta y. This is delta u with a minus sign. If we gain kinetic energy, it's because we've converted potential energy. All right. And so that's what we mean, in a sense, by can we define a potential energy, is when we work out the work that a particular force does, which is just the kinetic energy change, then does it matter what path it takes? And in the case of gravity, it doesn't matter. All right, what happens is if we happen to go upwards, we gain potential energy and lose kinetic energy, but to return to this final point, we give it back. So, non-conservative forces are path dependent, and so I've drawn a path here. And this example is going to be friction. Now, the example that I try to give in class is this. I have my hand here, I have my other hand, you can see the fingers of it here. If I move it like that, right? I move it like that once, I move the length of my hand. I've done some work, but I don't notice anything. If I move it several times, like I'm trying to stay warm, and then end up with the same displacement, my hands are warm. I've done more work. And that's because when we talk about friction, the friction is always opposite the direction of the motion. So what we can do is look at a particular point. Say we'll look here. The velocity is that way, and so the frictional force must be that way. We pick another point. Let's say we pick this point over here, and our velocity is that way, and so our frictional force is that way. Those are supposed to be in a straight line along that graph. So the point of this is we couldn't normally figure out how to deal with this, but if what we can do is say the length of this thing, the actual distance, we'll call d, is the path distance. And what we'll do is we'll cut this thing into little tiny chunks, dx, and each chunk will have a different frictional force, but each one will contribute. The little bit of change to the work is going to be the size of the frictional force times dx with a minus sign. I'm going to take work out of the system of this thing moving. And so we integrate. But this is going to be an integral along a path d. That notation might be a little weird if you're taking math. Don't worry about it. The point of this is that the work that the frictional force does is going to be minus the size of the friction force times the path distance. The larger this path is, the more work that is done by friction. Because your path could be a straight line, or it could be a curved line, or it could be a snake line. Or it could be, an example of warming my hands up, something where I go back and forth, back and forth, back and forth several times. So it's not the displacement that matters here, it's the actual path length. And that's the important bit. That's the bit that causes all of our other problems, but is why we even bother to get into using work and kinetic energy and potential energy. So this is out of your notes. This is one of the last couple of slides, I think. We do talk about power eventually, so I'll get into that very briefly in one more video, or maybe at the end of this one. We have a crate. It's 4 kilograms, and it's going to slide down a ramp. Right? You're loading it out of a truck, let's say. And at the bottom of the ramp, we have a speed. We'd like to know, what does friction do? This is not that hard. We can predict it with our idea of our work that friction does is minus the frictional force times the displacement, or times the distance. And we need to know what the friction force is. Well, it obviously accelerates. There's some acceleration here. And so we could do a free body diagram. Check that I'm putting everything on the camera again. Normal force, friction force, weight force. And so the part that goes along here is the sine theta component. And so we could get that, well, the friction force minus the friction force plus the weight times sine theta is mass times acceleration. So we could get that. But we don't have a good way of getting the acceleration, do we? I mean, we have initial final velocity and distance. Yeah, I guess we could. Yeah, so we can get the acceleration. V final squared is V initial squared plus 2a delta x. So a is V final squared over 2 delta x is 9.5 meters per second squared over 2 times 15 meters. So let's see, 9.5 squared divided by 30 is, so our acceleration is basically 3 meters per second squared. So now we can figure out what the friction force is, right? So we'll do the friction force is the weight times sine theta minus the mass times acceleration, which is mg sine theta minus a. So we'll have 10 meters per second squared times sine of 30 minus 3 meters per second squared. So what we have here is 10 times a half is 5, minus 3 is 2, 4 times 2 is, so our frictional force is 8 newtons. And so we have minus 8 newtons times 15 meters is 30 times 4 is 120 joules, the minus sign. So that's what we expect. But notice how much work that was. We started out with, oh, this will be easy. And then we had to go and figure out what this friction force is. So we did the free body diagram. We did Newton's second law. And then we're like, well, we got to figure out the acceleration. So we did kinematics and got the acceleration. And then we got the frictional force. And then we plugged in. Now, I propose that we can just jump ahead in the problem. Kinetic energy here is 0. The potential energy is 15 meters. So let's find E initial. 1/2 mv squared plus mgh. And what we're going to do is say h is 0 at the bottom, and so h here is 15 meters. This term goes to 0, so E initial is 4 kilograms times 10 meters per second squared times, well, actually, we don't know what the height is. There's an angle 30 degrees in here, so what we want is the vertical height. So it's going to be 15 meters sine of 30 degrees. It's going to be that vertical component. Well, that's just 7.5. So we'll have 40 times 7.5 is 300 joules. Right? So how much energy do we have at the bottom here? I'll do that in green. E final is 1/2 mv squared plus mgh. Well, h here is 0, so that term goes away. We'll just have 1/2 4 kilograms times 9.5 meters per second squared. All right, so 9.5 squared times 2 is 180.5 joules. So now we can say that the work that the frictional force does is E final minus E initial, assuming there's no air resistance or any other external forces. Well, this is 180.5 joules minus 300 joules is minus 120 joules. And I propose to you, now there's a little discrepancy here, and what's happening here is when I found the acceleration, right, it's not exactly 3, it's 9.5 squared divided by 30 is 3.0008. So this having a little extra term is accounting for that extra half a joule. I've rounded somewhere. But to get a close agreement here. But the point of this is, everything I did in black is doing it with forces and kinematics by itself. Everything I did in red and green is doing it with energy alone. And I think the red and green, the energy way of doing it, is simpler. For one thing, you don't have to deal with vectors. You don't have to deal with these forces. You just work out what's going on. So we're going to try this a few different ways. I'll do another problem here, and we'll see how things go. I am going to stop this video and start a new one.